Welcome back, everyone. And this week we're going to work on another sphere, and this one's going to be a hex sphere. Hex spheres are pretty cool because you can kind of do some really fun mappy stuff with it, especially like for games, because you can assign tiles and stuff. But it's kind of hard to build one for the most part. It's kind of a tricky kind of endeavor. I actually did it once. Didn't work out very well. It was almost good, but it wasn't perfect. And this weekend I worked on it some more, and I got a different version working, and it's a lot better, and it's a lot simpler how I encoded it. And so this is we're going to work on this. We're going to build a hex sphere, and we're going to build our hex sphere out of a icosahedron from our last video. Last video we made an isosphere. So we're going to start off with the exact same base that we did last time. I moved all the new classes like geometry, the new vec2s and vec3s. I threw them all into a new file called geo.js, and I modified quite a bit of things for this sphere to make it a little bit better, because I'm starting to like this little framework a little bit of how to handle things. And I created a new object called face. I'm not perfectly happy with it because I don't like the idea that I have to assign it back to geometry, because I need face to access vertices in a certain way. But for the most part, I'm pretty happy with this new setup I have here that I started with the last video. Some of the big landing changes is I changed vector3 back into a float32 array. Originally, for the previous video, was just a plain old array. Somehow, when I did addition, it started adding things up as string concatenation, and I decided to, you know what, that caused me a lot of problems, wasted a lot of my time, so I decided to switch it back to like how my other math library has a vec3 as float32 array. So this one, when I do addition, it's never going to do concatenation because it's always going to be an integer number. So it will never treat these as strings ever, because variables in arrays are just variants. They could be anything. And I made vertex extend vec3 instead of an array as well. So this way, all the functionality of a vec3, our vertex has that ability too. And I kind of, like I said, I fleshed it out. Even though I have two vector3 objects now in fungi, I'm going to redo fungi soon. So this vector3 style function object might end up replacing the old one, because there's some issues with it I don't like about it. But neither here and there. So I just wanted you guys to know we got all these new classes, or upgraded classes from the previous video. And so like I said, we're going to start off with like the same way. Everything kind of the same, but probably comment out some things we don't need. And I have something to call like shader inline, but we'll deal with that later. So we got a couple things. We got tiles. So this way we can have access to each face. So in case we want to do something with it, you at least have access to where each face is, or each tile, and what faces and vertices that are assigned to that tile. Face cache. Am I still using face cache? No, I don't think so. I think that was from the previous video. So I probably don't need a face cache. VMap, it's mapping vectors to faces, and this is our geometry class. And unlike the last video, we did everything in geometry. It's easier if we just start off with one, and then end up do our final changes in another geometry object. So we have two geometry objects. So what you see here is our regular icosahedron. It's the bare bones sphere that you can get with the least amount of triangles. So we're going to make a very, very simple bare bones hex sphere first, and then we do subdivision, and then we'll build up from that a little bit. For now, so we're going to start off with the basic icosahedron. So what we want to do to make life easier is a map vertices to faces. So if we go down here, map vertices to faces. And it's a very simple algorithm that I wrote. And the idea is that I go through every single face, every single triangle, and then I go through every single point. And for every point of every single triangle, I'm going to make a copy of the face. I'm going to clone it and make another copy. So this way, the reference, so it doesn't share references. I want to make sure it's in a copy, not like another pointer to the object. So, because I'm going to modify the face. So that means every, so then so the way it's set up is that I pass in VMap, which is a map object, and every index of the starting vertices is going to have an array. So that means every point is going to have an array inside the map, and it's going to correspond to the same index value of the vertice. So this way, I can say, if I'm, let's say if I'm at this point, I want to copy all these 5 faces to the array. Let's say that point is point 0. So VMap 0 becomes an array, and I want to put all these faces in that array. That's what I'm doing down here. And the only thing I want to do while I'm cloning it is I'm going to check to see the point that I'm searching for currently. Let's say I pick this face to start with, and that's the first point, and I want to find all the faces assigned to that point. If that point is not in the 0 position of the array, I'm going to use a new thing called, we had it in a previous video, but now I made a function out of it, move to start. So this way it moves that point to the start of the array. And it just rearranges it so everything stays in counterclockwise, so you can still render triangles, but it just rearranges it so this way the point that I'm asking for gets moved to the front and everything else gets rearranged correctly. So, and then we put, like I said, we end up putting it there. So that's the first step. So this way we have a nice big map of every vertex and every face that's assigned to it. Now the next step is, like up here, like I built every function as steps, like the last video. I want to sort all the faces. So every single vert face. So we're going to go back to the map. It looks like a long algorithm, but it's very simple. And this time I'm going to illustrate the concept idea. So now we have an array. So we have faces, right? So we have we're going to have, excuse me, I'm a horrible drawing with this tablet. So let's see. So the idea is that we have these 5 faces, and they're all assigned to this array that corresponds to this point. So we're just going to say, the way the algorithm works is like, okay, well, here's an array. So this is, let's say, 0, 1, 2, 3, 4. So I'm going to sort it. So well, you know what? No, it's not. Let's say this is 1, that's 2, that's 3, that's 4. Because now they're not sorted. Okay. So I'm going to go to the array and I'm say the array, face array for this index that I'm currently like this current vertex that I'm messing with, and I say grab the first face. So here's the first face, and I want to, since everything is sorted, so that's kind of like A, and that's B, and that's C. And since we've moved everything to the front, it becomes very predictable. This is also B, and this is C. For this face, B, and this also C. You know, as you can see, it's kind of like, I guess we'll say that if I was facing it, it would be it's the left face. So between the center point and the next element in the face array, because the face array is just is an array of 3 elements that corresponds to 3 vertices that makes a triangle face. The second one always goes to, it makes the left edge. So that means I can always grab 0 and 1 and give me the left edge. So I grab this triangle and I say, now find me in this list another triangle that shares this A and this specific B point. Now loops. You know, it goes to 1. 1 doesn't share it. It looks at all the 3 points. It finds A, obviously, but it doesn't find that specific B point. So it goes to number 2, and then it finds it. It's like, okay, we found it. They share this edge. That's what we're looking for. We're looking for shared edges. So now this saves into a new list and becomes the new number 1. Then I use this. Then I say, okay, well, now I want to use this triangle. Find me anything that connects to this point and to this point. And then the next one up finds this one. This becomes the new 2. Goes here. Finds it here. Oh, no, it finds this here. This becomes the new 3. Then when it looks off for this edge, it finds this in the new 4. And then eventually find sorted. So that's the idea, is that you're going to find the shared edges, and then every time you find a new triangle, you look at the edge between A and B and find the next triangle and keep going. And that is this gist of this algorithm. That's all it does. So we're going to have the ordered list and the old list, and we're going to have A and B that we're going to be searching. Now the interesting thing is to make this faster is that every time we find a triangle, we remove it from the list. That's what splice 01 does. It removes it from the list. Same thing here. Like once we find another triangle that shares the edge, we remove that triangle we just found, remove it from the old list. We're going to add it to the new list in the proper order. Then we're going to grab its A and B, reset the index, and then search again. So every time we find a triangle, the original list gets smaller and smaller. So this way it gets progressively faster searching. So so this way, and I'm not constantly searching all 5 triangles. So this way, by the time I hit the 3rd triangle, there's only 2 triangles left on the list. It probably is not that big a deal when you're dealing with arrays of 5, and I didn't bench press this to really see if it does a significant improvement by doing it this way. But if you're dealing with like in a previous attempt at this, I was doing this with tons of vertices, and I just kept pulling vertices out of the list, and that made things easier, a little bit faster. So this way, the deeper I get, the less there's to search. So. So step 2 is that once you have every face that belongs to every vertex in your icosahedron, you need to sort it, and you sort it by connecting every single triangle to something that shares the same edge, and it becomes a fan. It's just a fan shape. And now the final step is to create tiles. So I'm just going to create a regular tile. So I'm going to take all that information. Now if I click refresh, let's see. So I don't know if you can tell, but now during create tiles, there's 2 types of tile functions we're create. We're going to highlight. We're going through every single point, and every single vertex in our icosahedron is going to make either a hex or a pentagon. In this case, it's going to make nothing but pentagons because we don't have enough vertices to start creating hexagons. So the green dots are every vertex we start with the icosahedron. And then you'll notice there's points around them. That's because I'm going through every single face and finding the centroid point of that face. Right? So for every triangle, since we have that sorted array, we can then calculate the points. And now once we have those points, we then can connect those points and create a hexagon. And that's all. This also works if there's a hex shape. If there's a hex shape, the 6 faces would be sorted. We get the center of each one, and we connect. Now, the most interesting thing about this is, I don't know if you can tell, is that here's one hex, and the next point also has another, pentagon. And the next one has a pentagon, and you see they share these 2 points. That there's going to be connecting faces, because they share the exact same point. Yes. So yeah, we pass in our geo, we pass in our sorted map, and we have our G out, and we're gonna save tiles. And we use there's our I don't know why you call it FC. Oh, face center point. Yeah, face center point, face centroid point. Key because because every time we create a centroid point, it can be shared to another hexagon. So like this centroid point actually is connected to 3 different pentagons. So we cache these values in a temporary cache file. So this way we don't duplicate these vertices, because we're going to recreate these vertices in geo and in our new geo out. So we're going to create new vertices and new faces. That's why I said in the beginning we're going to have 2 new ones. So face vmap. So I'm treating so I'm trying to think. I'm blanking out now. All right, so for every vertice, we're calculating the new thing. So we're here. Even though I call it faces, they're not really faces. I'm considering this one big, all the faces here. So I'm gonna map it's really I'm mapping every face of a vertice. But so this is the point where I'm creating the green dot, and we create a new tile array that we're going to save into tiles. And tile is just going to be an array of faces that make up the tile. So we're gonna create. So at this point, I'm creating the centroid. I'm calculating the centroid. I'm making a key out of it by using a fixed value because of floating point errors. You need to kind of you need to round it up a little bit, because originally I was not rounding it up and it was causing me problems. And then I found out that the problem was floating point errors, because when you're dealing with floats, they're not perfect. So even though I do the exact same math, they might be at 0.00001 off, and then you have duplicate vertices, and then things get a little wonky. So if I round it up to 3, the precision becomes pretty good, and it works pretty fine. Because you'll never, unless you're doing really, really dense hex, this won't fixed 3 won't be an issue, because that means you're finding a point that's in a proximity area. So it works out. Like I said, it worked out pretty good. And if you have issues, you do fix the 2 or something. So that's a key. That's what I'm using as a key, and then I save the index to that vertice in that key. So this way, if I find the key, I reuse that point. Else, I create it and then use it. And for every point I create, I save it to a list, an array called edge, which just gives me the array of all these 4 points, or these 5 or 6 points. And then once I have at least, I think, 2 points, I can then start connecting the dots. So if I calculate, let's say I calculated this point. Okay, once I get to here, I have 2 points. I can then connect these as a triangle. I can make a face. And then I make the 3rd point, I connect those as a triangle, next point, next triangle, and so forth and so forth. And then when I'm done dealing with this point and its faces, I move on to the next point. Oops. If I can control the camera. So I move, let's say I did this point, then I just move on to the next point and rinse and repeat the process. And in the end, if I were to just output the final geo instead of the original geo, there you go. And now you can still see the points from the original icosahedron, and you see the points that are recreated. So the only issue is you end up creating a smaller sphere than you really end up starting with. But it ends up the other approach I did was I actually try to add faces and add vertices to a regular geo, and then connected the dot and find all the faces and everything, and that ended up creating certain edges that were kind of warped. when I started doing higher levels of subdivision. When I went doing it this approach, where I kind of do a centroid of everything and build it, like I guess a little bit smaller than the actual shape, the hexagons and the hexagons were a little bit more uniform. They're not perfectly uniform. Some of them will slightly be a little off. It's just not possible to make a perfect sphere. The more you subdivide, the greater chance that things will look less uniform. So it really depends on how heavily what level of the subdivision you do. Like right now, we're doing a 0 level of subdivision. This is the bare bones of a hex sphere, and that's really the gist of it. So the only last steps left to do is really to start subdividing triangles. And we're going to do a different way to subdivide triangles than in the previous video. So we're going to go, it's the same idea. We're going to take a triangle, right? Using the eraser end. So we're going to create a triangle. Or we're not going to create it. We're going to go through every single triangle and we're going to subdivide. Originally, we divided by half every edge, connected the dots, and made 4 different faces. So we end up just recreating all the faces, but just adding 3 new points to our vertex array, and that's how we did IcoSphere. And then we wanted to subdivide again. We went to every single triangle and we cut them up. And that was how we did subdivision. But that's not like a very efficient level of way of subdividing. This ends up just subdividing in a fractal pattern. And that's all that does. Now, if you want to have some level of control of how you subdivide, now we're going to say, well, how we want to subdivide, let's say, into 3 parts. Because if I did it the other way, we would always do 2, everything would be in 2s instead of 3s. So let's say I want to do 2 subdivisions. That means it creates me 3 segments. So that means I'm going to create 2 cuts, 1 here, 1 here, 1 here, 1 here. Now, we're only going to do the 2 cuts on the 2 edges. We're not going to do 2 cuts on the bottom. They might end up creating, but we'll get to it. So we're gonna have the triangle defined, and we're gonna cut the 2 edges. So this way we have ideally 4 points for every edge. We have the starting, the ending, and the 2 main cuts. We're gonna loop. We're gonna make a loop that traverses these 2 arrays, because that's gonna be 0 for both. That's 1. That's 2. That's 3. That's 1, 2, 3. So we're gonna loop for all the new points that we create on the edge, and we're going to then create another line between them. We're going to actually create a line between, ideally, technically, abstractly. So we want to connect the lines, and these lines they're going to also subdivide, but we're going to divide it depending on the row you're in. So if you're in, let's say, if you're dealing with 1, you say subtract 1, and how many subdivisions you're going to do? You're going to do 0 subdivisions. Here, if you're on 2, you say -1. That means you're going to do 1 subdivision. So you're going to create 1 point here. And then when you're in your final row, which is the final edge of the triangle, 3 minus 1 equals 2, and this is when you would actually end up making your final cut for the final edge. As you're building each row, you can then connect. Well, the row 0 is easy to connect. It's just the origin point for each one, and then the first element of each edge. That's done. In the next row, we connect these 2. Then we connect these here. And for a loop, we're going to do 2 at a time. So we're going to say connect here. We're going to start at the top. We're going to traverse it based on the top row. So you can look at these as top row and bottom row. That's what I labeled them. And then when we're rendering this line, this becomes the top row and that becomes the bottom row. So we're looping. So we create this one and we create this one. Then we check to see, do we have one more face to go? Or, well, then we iterate again. We connect these two. And like I said, we're going to create 2 triangles per. So we're going to check to see if there's any more vertices. If there's no more vertices, we're not going to create. So we move on to the next row. So we say this is now the top row, and this is the new bottom row. So we, again, if we follow the same pattern, so I guess we start at the top. We go this way. Then I think we start here and go this way. Then you check to see if there's points. So yes, there's points. So then you follow the pattern again, and which then you go here, here, here. And then the last iteration, you start at the last point, you create a triangle, you check to see if there's any more bottom points, you don't, you're done. You triangulated this as level 3. And this way allows you to subdivide. So by doing subdivision of 2, you create 3 segments. And that's pretty much the idea. Is you do subdivision, you create 3 segments. This way you can say, give me 3 subdivisions. So you 1, 2, 3. Now you have 4 segments, and you just repeat the loop over and over again. And that's how we're going to do subdivisions. So that's the new algorithm for subdivisions. So now, oh yeah, mind you, the way I'm actually creating tiles, I forgot to mention. We are trying. I forgot completely to mention that when I'm triangulating the tiles, because there's 2 ways you can triangulate a tile, right? One way, that's why I did it 2 ways. I want you guys to realize that. But one way, it makes it easier to do UV mapping. So now, mind you, I said at the end of the tile, we have an array called edges, and we have all the points. The simplest solution is, if you want to make as minimum amount of points and faces, you can take any point you want, which the easiest one, like mathematically, to do with loops. Let's say this is 0, this is 1, 2, 3, 4. Connect to that, connect to that, and connect to that. 3. So and the same thing when you deal with a hexagon. You can connect that way, connect that way, connect that way. This way you kind of basically make 4 triangles out of a hexagon, and you can make 3 triangles from a pentagon. Another way you can actually subdivide a hexagon, if you don't want to follow the pattern, you can kind of screwed up on that one. You can do that. You kind of do like a crisscrossy thing. You kind of just crisscross. So you can do it this way, where you have one center, kind of as a center point, and everything kind of branches out after that. Which this is an easy way to do in a loop. You can do it this way, which is more. I don't know. This is probably more UV friendly, I guess, because you can have at least a square here, and then you have the points up there. It might be easier to calculate the UV coordinates with this. And so there's like I said, there's 2. When you're dealing with hexes, this is the simple solution. I guess you could. Can you do it? No, you can't. It's no matter which way you do a pentagon. This is the only pattern you can use really to make a pentagon out of triangles. But you can use these 2 different patterns when you're doing a hexagon. But to make life easier and to only have one algorithm, I end up doing this way because it works for both, as opposed to this one only works for hexagons and doing a different one. So when I'm creating a tile, that's how I am actually triangulating. I'm triangulating that way. Because I probably forgot to mention. And that's why I need at least 2 points, because I'm triangulating it that way. And then we have fan tile, which is a different way to triangulate. Now, yet another way to do it. Now, this one is not the efficient way of doing things. Now, remember, I can do 3 and 4 faces to do a hexagon and a pentagon. Now a fan triangulation is that we need another point. So where the other one was more efficient, where we took those 5 edge points and then we just connect them with triangles, a fan triangulation is we create a new center point and we just connect everything from that new center point. Same thing works for a hexagon. So there's two ways you can triangulate. Like, it's essentially like this one. Now here's the thing, is that now I have 5 faces and 6 vertices. 5 faces, 6 verts, 6. As opposed to 3 faces and only 5 verts. So this costs more data, more things to render. That instead of rendering 3 triangles, now you're rendering 5 triangles. Now, I'm using this one in the final version simply because it's super easy to apply UV coordinates to this, because I can create a UV coordinate in a circular fashion. I can say that the center point is 0, 0, and every edge is a 1, 1. So when I create a shader, it's very easily to create circular designs in the hexagon if I lay everything out this way. And you can do some really fun stuff when you have a center point in a triangle. I'll show you that you can actually make spike balls and stuff. This is your honeycomb type of effect too, if you have a center point added to it. So even though you're wasting more data, it's easier for UV, and you can do some extra shapes that you can't do if you were to triangulate everything with the minimum amount of triangles and vertices. Like I said, you can't make a spike, because you need a center point to pull to push out. So that's why there's 2 tile functions. There's the efficient tile, and there's the fan tile. And we're going to really be using is the fan tile in the end. And they're almost identical. With the only added bonus is where I create that extra vertice, and end up calculating the centroid point, that center point that I want to use the connector. I calculate in real time instead of doing it after the fact. Yeah. And it so like with the other one, it was I had to be greater than 1. This is I is less than 0, greater than. So I only need 1 point to start triangulating, as opposed to need at least 2 points to start triangulating. And like I said, there's extra little bits here and there to make that tiling work. But overall, everything else stays the same. Like I said, and it just end up calculating that new point, and then making the triangles are different. Okay, so that's the one we're going to be using, and I have 2 subdivision functions. I think this was my very more complicated diluted one. I made for my first Hex Sphere that didn't work out too well. Didn't work out perfectly for me. But I have a new one that's a little simpler. There's a little bit less code. And I already stepped through. I drew the idea of what, you do the two edges, you subdivide them, and then you go row by row and connect in the dots. And this is the entire algorithm to do it. I think this thing can show you. Can you? I don't know. It's probably make a bunch of. No, it doesn't. Oh, because I didn't highlight it yet. So subdivide 1, refresh, and it looks a little bulgy, but that's because we need to sphere it. If I sphere it, refresh, now we have a hex sphere. We got some pentagons and we got some hexagons that connect in between. And that's really the gist of it. Step through a little bit of the code. So yeah, like I said, this is really the algorithm for what I drew out. And I use the same terminology. You got the left and right sides. We do a subdivide edge. And the subdivide edge uses the interpolation function, which makes it easier to determine. And it checks the cache to see, and it does that same fixed trick for caching. So we pass in the cache value. So yeah, you interpolate each component between vertice 1 and vertice 2. And you just create an array. So if I want one division, it's going to add the first point to the list. It's going to add the last point to the list at the end, and then it's just going to calculate the center points that you subdivide. So in this case, I starts at 1, and if you want to divide 1, it's just going to loop once. And yeah, like I said, it's just interpolation. So like I said, I took this interpolation function equation and I broke it out into this. I try to make it as efficient as possible so I don't duplicate anything. I don't duplicate much in any math that doesn't need to be duplicated. So, and I get rid of division. Oh, this is not division or something. I don't know. There is no division, but yeah. So TT. Plus array because division. I'm getting rid of division. That's why I have D inverted. Yeah. So it's basically, how. I forget T. That's how I calculate T, really. I times that. So if it's really 2 times that increment, 3 times that increment, whatever. We're just kind of traversing through the line using lerp and using time. We've done that before with tweening and other things. We use time to go from point A to point B. It's the mix function in shaders. We deal with smooth step, things like that. So yeah, that's how that simple function, how to subdivide. It looks more. It's only more complicated because of the caching. If I got rid of everything related to caching, like these 3 lines of code, or that pile of code, and a bunch of other ones in here, this function would be a lot less. It's really that caching mechanism that makes sure I don't duplicate the vertices that makes that function look a little more complicated. And then the subdividing triangles number 2, which is the better one. Like I said, we have the 2 edges, we have the top line. We create the top triangle. Like I said, I would say like row 0. There's no point in looping through it. It's just make it. And then you connect the dots. Remember I said you go from left to right, make that line, and then you'd subdivide it. You have that bottom line. And we start with the top line that I mentioned before. Yeah, and this is the part where we connect the first triangle, and then this is the second triangle. If t is less than t max, that means we have enough bottom row stuff, bottom row vertices to create the next face. And then at the end of that loop, we say the bottom line is now the new top line, and we rinse and repeat the algorithm. And we're all said and done, we add the faces into our geo. And that's how we do subdivision for a triangle. And there you go. And this is our, like I said, this is our sphere. So you can subdivide it more. Let's say we go to the next level of subdivision. And now we got more hexagons. You know, it's a bigger sphere, you got more points. So every single point, remember, like I said in the beginning, every single point becomes a new face. So every face you see here is actually a point that we create during subdivision. Like, so we have a geometry, we subdivide it, we move everything into we project it onto a sphere, and then we start mapping every single face of the original. If you you know what? Let me explain it first. At this point, during these 3 lines of code, we're creating an isosphere. Right? So that's what we're doing. We're actually creating an isosphere, just like in the previous video. So those 3 lines, those three operations creates an isosphere. These final 3 transforms that isosphere into a hex sphere. And there's actually a name for it. I forget what they're called. Geodisk sphere, geodisk sphere, also known as the Goldberg polyhedron. A lot of names for it, but most people will call it the hex sphere. A sphere made out of hexes. So yeah, so if you want to think about it that way, we're rebuilding our isosphere and then taking every point of the isosphere and converting it into hexes and pentagons to create determine all the faces on here. And that's it. And to spheres, it's easy. It's same. It's exact. That function hasn't changed since the last video. We just normalize it. That's all. It's a normalization. That's all it is. If you want, and one thing you should take note: the 12. Remember, the isosphere starts with an icosahedron. An icosahedron comes with 12 vertices. Those 12 vertices will become the 12 pentagons in your sphere. So in this sphere, there will be 12 pentagons within a sea of hexagons. So those 12 points that start off your icosahedron will always be there. No matter how many times you subdivide, those 12 will always be there, and they'll always be in the exact same spot, just moved further away, projected on the sphere. So what else we got? At this point, you can start playing around with it a little bit. Like I think I made debug, so this way I can see all the hexes. Click refresh. The pentagons highlight simply because they're surrounded by hexagons. That's why I have debug pents. This way we can visually see where all our pentagons are. There you go. Now we can easily find the 12 pentagons that we have hidden within our sphere. Those debug functions are pretty easy. All I do is I go through the tile. Remember, I have tiles. Oops. Like I go to hexagon and pentagons are the same thing. And I just draw lines between all the points. So you have the each face, and I just go to the first element, I think. Oh no, I connect the dots. So it's the bottom of the face of every face. So every face is a triangle. So I just draw a line, the bottom edge of the triangle, which then forms the hexagon that you see. Because I'm only doing to the faces, I'm only doing to tiles that have basically 5. So if it's not 5, don't do it. So I'm only gonna, if it has only 5 vertices or 5 faces, it's a hexagon. If it has 6 faces, if it has 5 faces, it's a pentagon. If it has 6 faces, it's a hexagon. So so that's that. It's very easy, just some fun stuff to play with. Now since we're using the fan tiles, which has a center point, we can control the center point and do some stuff. So let's see, the sphere is at a range of 2, so we make a range of 2.2. So we're going to move the center point, and if we refresh, there you go. Now I know this is a fruit that looks like this, but you can go really crazy. You can make it look bigger. There you go. Now it's like a spike ball or whatever. If I want, I can just shrink it down to less subdivisions, so there's less points. Or don't do any subdivision whatsoever and just stick with the starting icosahedron. And you got this shape. You know, like I said, at this point you can start playing around. Let's stick with that. You can go inverted. You can say maybe 1.9. Probably can't tell. Refresh. There you go. So now the points are going inward, kind of for some kind of, I don't know, circular speaker type of thing. I've seen speakers that are kind of like that, look like that, but has less hexagons and pentagons. And the last thing we can do is apply UV tiling to it. And remember, like I said in the very beginning, that using the fan tiles is easier because I can make the center point 0 and then the edges all 1. So if I were to switch over to this VAO that uses the final, it has the UV applied to it. Click refresh, and oh, and I gotta switch it to the other texture, the hex texture, or not texture, hex shader. And there we go. Look at that. Look at that. So now that we have the UVs applied to it, we can do some fun designs with it. So if you want to see how the function really looks, like I said, we pass in the tiles, which has every face, and like I said, center point actually gets a value of 1, and the edges get a value of 0. I got it reversed, but that's where we'll have it set. It doesn't matter which way you want to do it. And remember I said I have a new function in shaders, which says inline. So instead of keeping the shaders as text files, I can actually put them as script tags and then just render it like normal. I think the only difference is I have these flipped backwards. It's just because of my code editor highlights things horribly when they do it correctly. So I end up changing it for inline. The ending tags have to be written this way so I can kind of keep the highlighting better so it doesn't look so bad. And this is the shader I'm using. Very simple, basic vertex shader, and the fragment shader allows you to do, it's like I said, I'm just checking between the 0.0 and 0.1, and since x and y are the same, I just have to check for one value, which I'm using x, and I just combined it. So we've done things like this in the past, so I don't need to explain the shader too much, but as you can see, I'm just using this function over and over again and defining different defining different radius. So if you think about it as a circle, that's how I'm doing. But since everything's the shape of hexagons and pentagons, here you go. And you can always change things too. Like I can change this to thickness can be 2. I made it thicker. The fade is just to create that little blurring near the edges. It's kind of like anti-aliasing. If I say 0, then everything becomes pixelated. So, yeah, I know I said I wasn't going to explain this, but just so you have an idea of. So yeah, and like I said, I just combined C, and that's very simple. and that's just, like I said, that's the shader. And then for last bits of funsies, like I said, you can play with it. You can then do the tile length. 2.5. 5 maybe. Refresh. Now it's gonna look like a little like water mine, like underwater, like that blow up ships and submarines. If I do it inward, like I said, now it looks like a speaker type of thing. Speakers kind of look like somewhat like that, not really. I just think they do. I don't know. And let's say you can subdivide 5, and let's make the sphere a little bit bigger so we can make space. Ooh. Let's not change it. Refresh. And there's our much bigger sphere. There's our hexagon sphere. I think the higher you go, like I said, the greater chance that each hexagon might get some deformity. But this one seems to do a decent job. It's not going to be perfect. The closer you get to a pentagon, you might see some distortion. Like you can see this distortion here a little bit now. Like this one definitely doesn't look uniformed at all. Some of them aren't. Like this one seems a little more skewed. So you're not gonna make a perfect one. It's not really possible to make a perfect one where every single hexagon is perfectly uniformed. I spent 2 weeks essentially reading and trying to fixing this and trying to improve it. There's no easy way to do it. And like I say, the higher the subdivisions, the less uniformed things are gonna get. So, but depending on what you do, and sometimes you might not even notice it unless you're really, really looking for it. So there you go. So refresh. There you go. So you get a nice full screen view of the hex sphere. And like I said, from a distance you can't tell. Might be cool to play games. You can click on the spot and make a character move to that spot. You can do some kind of weird 3D planet chess game. I know there's games that you do hex. I forgot a thing called Colonies, or I don't know. There's like games that you can take over territory, and that hex spheres are good for that. So you can kind of do that colonies. You own that plot of land, and you're going to invade that plot of land, and whatever. I forget what those games are called. I've never been into those kind of games. I forget what they're called. I forget. There's like a really popular name for one of those games. But I probably made this video too long, so here you go. Hex spheres. All the code is up in GitHub, and or should be up in GitHub sooner or later. And yeah, I hope I managed to explain to you. This was kind of a pain in the ass to do. There's some people who commented on Twitter. I forgot your guys' names, but thank you very much. Stuff, suggestions, and sending me links to some demos and things like that. If you are, thank you a lot. I'm sure I thanked you on Twitter. So yeah, my throat's starting to hurt. So I'll probably just stop now and not talk anymore. So the usual BS, like and subscribe. It helps this channel. Almost at 1,000 subscribers, so I might start getting features. I think I can do live streaming on YouTube once I get 1,000 subscribers. Maybe it's something I can do if you guys want. I can do some night live coding. Yeah, I might do something like that. Maybe I might do that if I get that. I have something I want to do, so maybe I'll do like a night coding, and I'll just do it live, and people can watch me break code. Once I get that functionality and that feature, or I can just go to Twitch, I guess. I don't know. I don't care. I don't think people care to watch me code. They just care about the end results. You don't want to see me make a bunch of mistakes. I already make enough mistakes when I make these videos. So that's it. I'll see you guys in the next video. The next video is going to be kind of cool. I already have all the code down. Maybe I'll record it today, or maybe I'll record it tomorrow. See you guys.